Hello, this is Tracy. Welcome back, Math 135. We are in Chapter 7, the central limit theorem, and how that applies to the sampling distribution of the mean. You have hopefully already looked at some videos that talk about what the central limit theorem is and why it's so important and how it works and all that good stuff. What I want to do is go through an example, a sample problem that applies the central limit theorem and the sampling distribution of the means. So here our example. In 2004, a water taxi sank in Baltimore's Inner Harbor, killing 5 and injuring 16. The safe passenger load for the water taxi was 3,500 pounds. At the time, it was believed that the mean passenger weight was 140 pounds, based on data from 1960. Based on that 1960 data, the taxi was allowed to carry 25 passengers. In 2004, it was found that the weights of men in the U.S. were normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. Now, in 2018, average weight for men is closer to 196 pounds and women is 169 pounds. Suppose the safe limit was set to a maximum of 20 passengers, assuming an average weight of 175 pounds. Now, the reason we're looking at men is because we want to think of what's the worst case scenario. Some convention comes into town and that water taxi actually has all male passengers. So we are looking at a maximum safe load of passengers based on all being men with an average weight of about 175 pounds. Because if you take that 3,500 pound limit and divide it by 175, we get 20. So 20 passengers max. And hey, there's a little wiggle room. That's even a little bit more than the male average. So in 2004, suppose that 20 male passengers boarded a water taxi. We want to answer two questions. What is the probability that a randomly selected male passenger weighed 175 pounds or more? And what is the probability that the mean weight of all 20 passengers was 175 or more? In other words, what was the probability of overloading that water taxi in 2004 if 20 men boarded? So here, this is what we would be looking at. Our population for male weights in 2004 was normally distributed, and we had a known mean of 172 and a known standard deviation of 29 pounds. So that would be represented by a graph, the probability distribution shown at the lower part of the graph, the low, short, fat normal distribution. The sampling distribution of the sample means what the normal distribution would be if we took a whole lot of samples of size 20, found their mean weight, and then plotted those mean weights in a distribution. We would get an approximately normal distribution like the tall, skinny, red normal distribution. It would have the same mean as the population distribution. The peak would be in the same place, but the standard deviation would be much smaller, making that a taller, skinnier normal distribution. So our first question, what is the probability that a randomly selected male passenger weighed 175 pounds or more? So here we have that normal distribution, and we show the mean being there, the little slash mark in the center at 172 pounds, and then we look at all of the area to the right of 175. And we want to know what that area is in this normal distribution because that will tell us the probability that a randomly selected man has a weight of 175 pounds or more. So now we are not going to do this by hand. We are not going to use some crazy table in the back of some book or anything like that. We are going to use our calculators. So in our calculators, to find the probability that that X value, that random variable x, takes on values of 175 or greater, we would go into our distributions. So in our calculator, we hit second vars, and that takes us to the DISTR, the distributions. When we do that, you will see a list of distributions. So you will go down to the normal CDF because we want a cumulative distribution function. So normal CDF, and the first thing we will put in is the lower bound. The lowest area we are interested, or the lowest weight we are interested in, which is 175 pounds. So we want to know the probability of weighing 175 pounds or more. So the highest weight we'd be interested in, well, just stick some really huge number in there. Weights we are assuming theoretically can go up to infinity. We know that's not reasonable, but just stick a huge number, 10 raised to the 99. That's a big number. That works in our calculator. Comma, the mean weight for the population, 172, comma, the standard deviation for the population. And as we see in our picture, we see that that area to the right of 175 is 0.4602. And what that tells us is that the probability that a randomly selected man in 2004 weighing 175 pounds or more was approximately 46%. The probability a randomly selected man in 2004 weighed 175 pounds or more was approximately 46%. Our calculator told us that. We used the normal distribution for the population of men who had an average weight of 172 pounds and a standard deviation of 29. Now, though, suppose we want to know the probability that the mean weight of all 20 male passengers was 175 pounds or more. In other words, what was the probability we overload that water taxi in 2004 if 20 men boarded? For this, we would not use the population distribution anymore because we are not looking at the probability of selecting a single person from the population with a weight of 175 or more. We are looking at the probability that the average weight of those 20 men would be 175 or more. So we would use the sampling distribution of the sample means, the taller, skinnier distribution. And this taller, skinnier normal distribution has a mean of 172, the same as the population, but the standard deviation is smaller. It's going to be not 29 pounds, but 29 divided by the square root of 20 pounds, where 29 is the standard deviation for the population, and 20, that number under the square root, is the sample size of the 20 men that we are gathering on our water taxi. Now, note that n equals 20 is okay. That's a fine sample size because we know that our sample is drawn from a population that follows a normal distribution. Otherwise, n would have to be 30 or higher because 20 is just too small for the sample means to fall into a nice normal distribution. So now, what is that probability that the mean weight of all 20 passengers was 175 or more? And remember, that tells us that the total weight, 175 times the 20 passengers, would be 3,500 pounds or more, and overload that water taxi. So pop that into your calculator. Here we want the probability that x bar, the mean weight, is greater than or equal to 175. But in our calculator, we go the same place. Second vars to that distribution. We want the normal CDF. We still want our lower bound to be 175 pounds. We still want our upper bound to be something ridiculously huge, like 10 to the 99. We still want our mean to be 175, but now we type in a standard deviation of 29 divided by the square root of 20. And in your calculator, you can do that. Actually type in that normal distribution. 29 divided by the square root of 20 to let your calculator round as far as it can. Avoid rounding error. And that answer turns out being about 0.32. In other words, in 2004, the probability that we would have overloaded a water taxi with a safe capacity of 3,500 pounds if all 20 passengers were men was about 32%. About 1/3 of the water taxis carrying all men would be overloaded if we had 20 passengers. Wow. Okay, so here was an example of using the central limit theorem and the sampling distribution of the means. That's what we used for question number 2. All right, well, talk to you later.